Hi, everybody. So I've been asked to do number 12. I'm sorry, question 1 from section 12. So just a real quick read through. In 2012, the Pew Research Foundation reported that 45% of U.S. adults report that they live with one or more chronic conditions. However, this value was based on a sample. And because it says it's a sample, this is a p hat. It is not a p. So it may not be a perfect estimate for the population parameter of interest on its own. And when that happens, we often try and generate a confidence interval, which is what we're going to end up doing. The study was based on a sample of 3,014 adults, and below is the distribution of 1,000 bootstrap samples, sample proportions from the Pew data set. Okay, we talked about how the bootstrapping takes the results, shuffles them again, and so forth. All right, so a couple of things. If we take our p hat, which is 0.45, and we generate our q hat. Now, our author uses 1 minus p hat instead of q hat, but they are often used interchangeably. So you'll see some notation where it says 1 minus p hat, but then they also call it q hat. And then the relationship between p hat and q hat is that they have to add to 1. So if p hat's 0.45, q hat is 0.55. Now, I'm going to come back over here for a second. I'm going to scroll down and note that we are trying to do the 98% confidence interval. So what I need to do first is check my validity constraints. And to do that, I have to make sure that this value and this value multiplied by 3,014 will be larger than or equal to 10. And if you do that, you'll get significantly larger than 10. So we can go ahead and use a model-based approach. So the standard error, if we're running a hypothesis test, we have a proposed null hypothesis distribution, and we operate as if that's correct to try and run the test. But in this instance, because we're trying to get a confidence interval, we are using the sample values in our P and our Q when we're trying to generate our standard error. So we're going to be taking 0.45 and 0.55 and dividing it by 3,014. So we're going to have our standard error, but we're also going to have our multiplier. Those two things multiplied together will generate a thing called the margin of error. Now, how do we get this z sub 98, our multiplier? Well, it's often the case that you'll see z sub 95, z sub 98, z sub 99, z sub 90, and they just write the confidence level down here. And what that means is in the middle of the normal curve, you have 98% or 0.98, and it's balanced evenly on a symmetric curve. So the left side will match the right side. And if I put 0.01 in that tail and 0.01 in that tail, it would make sense that these three values add up to 1. So if this was 95, we'd put 0.025, 0.025. If this was 90, we'd put 0.05 and 0.05. Hopefully that makes sense. If we're doing the calculator, we'd be using second VAR's INV norm. Our 0.01 is the area in the left tail, and then we put our mean as 0, and then our 1 as our standard deviation, and you'll get negative 2.326. Now, I'm going to pause for a second, and I'm going to come over to the computer, and we are going to go here to, and you would click on randomize, then you would scroll down to model-based inference. You would click on calculate the confidence interval multiplier. You would change that to 98. You would hit return. And then you'll come over to the right-hand side and you'll see there is your 2.326. Okay. Hopefully that makes sense where we're getting our multiplier from. So we're back over here and we are looking at our computation, in fact. So we're taking our p hat, q hat divided by n. We are getting our standard error here. So when I punch that into the calculator, I get about 0.009062. Our question was about sort of tolerances. So I kept this value. I didn't convert it to the 0.01 in the computations because I'm a little concerned that we might have some accuracy issues going on. Remember that the confidence interval is going to take the point estimate, our p-hat, and we're going to add and subtract the margin of error. So what this is going to look like is we're going to take 0.45, that's our sample proportion, our p-hat, and we're going to add to that 0.009062 times 2.326. Now, this is our standard error, and this is our multiplier. Now, I have it out of order. I should have had the 2.362 first and the 0.009062 second, following the pattern where you have the z-score or the multiplier times the standard error, but multiplication is commutative, so hopefully you're okay with that. So we're going to do 0.45 plus that, and then we're going to do 0.45 minus that. And these are the two values that I get. I have 0.4289 and 0.471078. Now, just to show you, and let me get this back. Click. There we go. Okay, so the boundaries for, or the tolerances for the lower limit are from 0.425 to 0.435, and we got 0.4289. Here, 0.465 to 0.475, and we got 0.471. All right, now, we have not discussed this yet, and so if this video gets transferred to later semesters, hopefully we will have discussed these ideas a bit more before we get to this spot. But confidence interval is different than a probability. What's going on is that if we were to run this process, so many times, we would be looking at a distribution of all of the possible values of our, how do I say this well and not have a visual for it? And this isn't the visual I'm looking for. If we did 100 confidence intervals, approximately 98% of them would actually have the real population value in the interval. About, you could have down to like 95, or you might actually capture all of them, but it's somewhere around 98. And because it's somewhere around 98, we don't call it a probability. We call it a confidence level, okay? So we would say that we are 98% confident. It's not probability, it's not chance, but we are 98% confident that the true proportion of the U.S. adults will be between, and it's just the tolerances from there. So it would just be whatever our number was in this first box, and then whatever our number is in the second box. Okay, I hope that helps.